Hello, everybody. So today we want to talk about some advanced CNN architectures and also some famous transfer learning models. Um, next week we will talk about maybe RNN with some examples. I uploaded the slides to Blackboard already. So if you want to go through it, because many people are working with time series problems. So today I want to talk about some advanced CNN architectures. So I need to cover some ideas or some topics. Number one is CNN design pattern. I mean, there is a pattern which people follow when they design their convolutional neural network, and also understanding some advanced architectures, which is very famous, like, for example, LeNet, AlexNet, VGGNet, Inception, ResNet, etc. For the CNN design pattern, I mean, there are three patterns. Number one, it's feature extraction and classification. This is a traditional one. So when we design CNN model, in fact, we try to focus on part for feature extraction and the other part for classification. The second pattern, it's image depth increase and the dimension decreases. Some people focus on increasing the depth and decreasing the dimension of the extracted features, for example, or the feature maps. So you have some specific dimension of your input image or input volume, and you try to increase number of feature maps or features it's extracted. So we try to increase the depth with time, and also at the same time we try to decrease the dimension of each feature map, the dimension which is height and width, for example. Pattern number three, it's just fully connected layers, which we are familiar with. So we will start first with this feature extraction and the classification pattern. It's composed of two parts. The first part for feature extraction part, which is the convnet, which consists of a series of convolutional layers, and the classification part, which consists of a series of fully connected layers. So usually people, when they design their convnet, the first part, which will be for feature extraction, and the second part will be fully connected layers for classification, right? So, so you can use some number of layers, some conv layers, for example. Maybe also each layer should be followed by maybe some dropout, maybe also by some um, max pooling, for example, right? So it could be followed by pooling layer, conv followed by pooling layer, and so on. So the first part will focus on feature extraction, and the second part will focus on classification. I mean, this feature extraction part, this is very important because people in transfer learning, sometimes in this part, it takes too much time and it requires too much data for training the feature extraction part. So it should be possible if you have a model which has been trained for solving some specific problem to transfer it to another problem by importing the feature extraction part and modifying maybe this classification part. So we can keep that part and freeze it so we don't retrain it again and just add a new classification section or layers. So this is pattern number one. Pattern number two, here we try to focus on the depth of the extracted features, or we can just call it image depth. So we try to increase the depth. Do you see? Depth here means number of channels or number of extracted feature maps. So for example, the input volume here is to 224 pixels times 224 pixels, and maybe it's RGB image. When it's RGB image, it means the depth here equals 3, right? So this is the input volume, and after that you will apply some convolutional layers, for example, and each convnet will be followed maybe by some max pooling, for example. So in this case, we will try to focus on reducing the dimension of the extracted feature maps and increasing the number of extracted feature maps or the depth. And we will do it for some layers until we reach some number. For example, here at the end here, we have as a dimension of the extracted feature maps will be 13 times 13, but the depth will be 384, for example. So here we try to focus on increasing the image depth and decreasing the dimension of the extracted feature maps. So the input data at each layer is an image. It could be an image, and it could be also, when it's a feature map, we can just consider it as an image, right? But it will have a depth of 1, right? So the input data at each layer can be considered as an image. At each layer, we apply a new convolutional layer over a new image, and each image is a 3D object that has height, width, and depth, right? So here, for example, you can just imagine that this one is an image which has a size of 55 times 55 times 96, for example, right? You can just imagine that it's an image, a 3D image of this size, for example. So the input here, it was 224 times 224 times 3. So the input image here is 224,224,3, because it's RGB image. And the next layer, we will get also from the next layer an image of this size, and we will do it in this way. So, but the focus here is to increase the depth, which is which is referred to the number of color channels, for example. And when it's depth 1, it means it's a grayscale image, and when it's a 3, it means it's RGB image. In later layers, the images still have depth, but they are not colors; they are feature maps. So here, in fact, it's not color. I mean, in the input volume here, the depth here means color, one called red, green, and blue. But for in the later layers, it's not colors, but it's feature maps. This is the total number of feature maps which we want to extract, right? And this is the size of each feature map. So the idea here is to focus on increasing the depth and decreasing the size or the dimension of each extracted feature maps. In this pattern, the image depth increases and the dimension decreases. So this is one pattern, for example, where people try to focus on. Pattern number 3, it's a fully connected layers, and this fully connected layers, we use it for decision making. It's very similar to shallow learning. So this part is very important, this fully connected layer, because this is a part which will make decisions. In fact, this is a part which will make classification. So you can just call it's a classification layers. So if we go back here, we have the feature extraction part and the classification layers, or the classification part. I mean, in this feature extraction part, we can go for pattern 2, for example, where we try to focus on increasing the depth and decreasing the dimension of each feature map. And finally, we have this classification part. And also this classification part, it will be like this one also. We will start with big number of units, and it will decrease until the last layer where we make some decisions, for example. So the fully connected layers, it could have the same number of hidden units or decrease at each layer. Usually it's a decrease, in fact. Number of units decrease from one layer to layer until we reach the output layer. So it's rare to find a network where the number of units in the fully connected layers increases at each layer. So, I mean, here's the idea. For example, it could be MNIST dataset, for example. Do you remember MNIST? If it is MNIST dataset, we have 10 classes. So people usually, they follow this one. So they start with big number of units here, big number of neurons here in that part, and it will decrease with time until we reach here. We have here 10 classes, for example. So this is the most general case where which people usually follow when they design the fully connected layer part for classification. And of course, maybe in the last layer here, I mean, the activation function, it's up to you to select. Usually here we use ReLU when it's image, because ReLU, it will map all inputs, positive inputs into the same numbers, and the negatives will be converted into zeros. But when it's image, I mean, the pixel value is a positive number. So you can use ReLU here. You can use, for example, ReLU here. And in the last layer here, we can just call it, softmax layer. You can just call it softmax, right? When it's softmax, means we can try to predict the probability that this example belongs to this class, and so on. Yes. Yes. So do you have any question for those, design pattern, for example, in CNN? So we have pattern 1, pattern 2, it's feature extraction and classification. This is the most traditional way. Pattern number 2, we try to focus on image depths we try to increase the image depth or feature maps depth and decreasing the dimension, because we will end up with flattened layer, and after that we will use a fully connected layer. So we'll try to decrease the size of the first fully connected layer as much as possible to avoid overfitting problem. Because if we will get overfitting, we will get overfitting from that part, from the fully connected layer. And it ends with this fully connected layers, and the design here usually it could be just the same. We can just use the same number of units in each layer, but usually people start with big number, and this number decreases with time until we reach the output layer. Yes. After that, we have a set of those advanced architectures which people has been designing and people are using. Usually, we call it transfer learning. So we have those design pattern. People designed those famous neural network, and they used it in various different applications. They trained it with some of the most famous or most very large public data sets. And we can import those models, and we can try to modify it and use it in our own applications. So we can start, for example, with this LeNet. This LeNet, it's introduced in 1998, in fact. So it was one of the first famous models. And this LeNet, the architecture is composed of 5 weighted layers, and therefore they call it LeNet 5. And mainly it comes from the author. His name is Lekan et al. And it's called LeNet 5 because it consists of five layers. 3 convolutional layers and 2 fully connected layers. So the LeNet 5, it consists of 3 convolutional layers and 2 fully connected layers. And this is its application for MNIST dataset, for example. So we start with 3 convolutional layers, and followed by 3 fully connected layers. And in the last fully connected layers, we try to classify each image into 10 classes. So at the end here, we have 10 classes. So we start with, the first conv layer, it has a filter size of 5 times 5. And when you apply this one to this kind of image, with the stride equal 1, maybe with 0 padding, because we have 0 padding because the same size of the feature map has the same size of the input volume. And we try to extract 6 feature maps here. So the size of the feature maps from the first conv layer, it will be 28 times 28 times 6, which means we'll try to extract 6 feature maps. And after that, we will use average pooling. From this average pooling, we will get this dimension. It will be 14 times 14 times 6, right? And after that, we will use another conv layer with the same filter size, 5 times 5, with stride equal 1. But here, we didn't use mapping, 0 padding. So the size of the volume, it will be 10 times 10 times 16. So here we need to extract 16 feature maps from this input volume without 0 padding. So the output will be 10 times 10 times 16. It will be followed by average pooling again. So from this one, we will get 5 times 5 times 16, correct? And again, we will use convolutional. This is from average. And after that, we will use another conv layer. This conv layer, it will produce. Okay. So first, we started by this one. We will apply here convnet. We will get this one. Right. And after that, we will have another convolution. So we will get this one. And after that, we will apply 5 times 5 times 16. So we will get this one. I don't know. Subsampling. It's subsampling, right? Can you see the 3 convolutional layers here? Conv 1, we will get this one, this feature maps. And after that, yes, okay. So we will get this one from average pooling. We will get this size, and we will apply convolutional again one more time and flatten it to get those 120 pixel values. And it's followed by two fully connected layers. This is the first fully connected layer. This is the second fully connected layer. So the number of weights here, number of units will be 84. And in this case, number of parameters here, it will be 84 times 120 plus 84. And the last fully connected layers, the number of classes will be 10, right? So now we can, so in fact, this one, it consists of 3 conv layers and the 2 fully connected layers. But maybe it's not very clear here because this one will be the third convolutional layer. This one, the third convolutional layer. This one, it's the second. This one, it's the first convolutional layer. So the output from the first convolutional layer and average pooling, it will be 6 feature maps of size 14 times 14. The second convolutional layer, the output will be 5 times 5 times 16 feature maps. And we will apply again convolutional and flatten. From this one, we will get 120 pixel values. Yes. Here they used hyperbolic 10 as an activation function instead of instead of the art ReLU, and because ReLU at the time has not been used in deep learning. So here, those fully connected layers, they use hyperbolic tangent. They use hyperbolic tangent activation function, not ReLU. So this is LeNet. Yes. This LeNet here, I have an example here. I used it for classifying MNIST datasets. So this is the code. If you want to go to the code, and we can achieve an accuracy equal to 98.7% in 20 epochs. So I trained this model, in fact, for 20 epochs. So this one, it's not transfer learning. In fact, we build it as LeNet, in fact. So I build it as a LeNet. So the input shape was 28 times 28 times 1. The output shape from the first convolutional layer, it will be 28 times 28 times 6. And after that, we apply average pooling. From this average pooling, the shape will be 14 times 14 times 6. We will apply the second convnet. From this one, we will get 16 feature maps of 10 times 10. Apply average pooling again, so the size will be 5 times 5 times 16. The third convnet, we will get 1 times 1 times 120, in fact. So this is the third convolutional layer. So here we will get 1 times 1 times 120. So the input volume will be 5 times 5 times 16. We need to extract 120 feature maps without using zero padding. So the output volume will be 1 times 1 times 120. So we will get 1 pixel. Each feature map will be represented by 1 pixel. We will flatten it. So we have this flattened layer here. We will flatten this one. So we will get 120 pixel values. We will have 2 dense layers. The first dense layer, it will have 84 units. So number of parameters here will be 84 times 120 plus 84. That will be this number. The second dense layer, it will be the classification layer. So we will have 10 units because we have 10 classes. So the number of parameters here will be 10 times 84 plus 10. Yes. What about, can you calculate this number? Number of parameters here, 156. How can we get this number? We can get this number from this, we used here 5 times 5 times 6, right? 5 times 6. So 5 times 5 times 6 plus 6 should be 156, correct? Yes. So it should be 156. So this 156, because the kernel size, it's 5 times. In fact, it's 5 times 5 times 6 plus 6. So it will be like this one. Yes, and if you want also to calculate this one, it will be 16. We need to extract 16 feature maps. So those 16 feature maps, and the size will be 5 times 5. So it will be 5 times 5 times 16 times 6 plus 16, right? Can you try to calculate those numbers? So because I mean the filter size is fixed, it's 5 times 5 each time. So it will be 5 times 5 times 6 times 16 plus 16. So it will be 2,416. So this number, if you want to get this number, it will be 5 times 5 times the number of feature maps of the input, which is 6, times the number of feature maps which we need to extract, which is 16, plus the bias, which is 16. So it will be this number. This one, it's in the same way also. This number, it will be 120 feature maps times 16. Okay, times the filter size, which is 5 times 5, right? So it would be 5 times 5 plus 120. So it should be also this number. So I try to calculate this number. So it will be 120 times 16 times 5 times 5. Okay. Plus 120 bias. So it will be the same number 48120. Yes. So so this is a LeanNet 5, and I used it for for classifying this image data set, and this is a training and validation loss, and this is a training and validation accuracy, and you can just see that we don't have any kind of maybe overfitting here. Training and validation accuracy, we can see that at some point here, the validation accuracy increases. In fact, so this is in fact a very ideal model for classifying MNIST dataset, and we can achieve this very high accuracy. And we have here this confusion matrix, and from this confusion matrix, we can see where the model is confused, and it's normal. I mean, it's totally okay. So, for example, the model can classify, for example, or misclassify. It can misclassify. Maybe this is the true, this is the predicted. So, for example, here we have some confusion between 4 and maybe 4 and 6, 5 times, right? For example, 2 and 6 one time, maybe 1 and 6 two times. So those are the this is the confusion matrix, which is, I mean, yes. So do you have any question for this LeanNet 5? Any questions?
I have one. Is it only for processing the pictures, or can it be used for other types of problems?
I mean, do you know, in convolutional neural network, usually you are working with images. I mean, it's meant originally for images, but you can just use it for any kind of applications. If you want to use it for text, for any kind of, so it's up to you. I mean, so the application, you need to modify it to the application which you want to do. But usually, I mean, deep learning, it's done for originally for images, right?
Yeah. Okay. Thanks.
Yeah, because those convolutional neural network, I mean, those convolutional layers, they are meant for extracting some feature maps from images. So we have the original image, which is 3, for example. This is handwritten digits. From this one, we will try to extract some feature maps. The feature maps here, it will be 6 feature maps, right? By applying the filter size, it's 5 times 5. So this is the filter size. We will apply this filter size to this input image 6 times, and we will get 6 different feature maps. And after that, we will apply in the second convolutional layer, we will apply the same feature, the same filter, which is 5 times 5. We will apply it 16 times to the extracted feature maps, to this one. So when we apply it, we will get 16 feature maps of size 10 times 10. We will do it for the third time. In this case, also using the same filter size, which is 5 times 5. From this one, we will get those 120. We will get 120 feature maps, which has a size of 1 pixel, only 1 pixel. So the size here, in fact, would be 1 times 120. And we will flatten it to get this one. And after that, we will feed those pixel values to the two fully connected layers to make classification. So the application, we should have some examples. For example, how can we work with text? But I had a presentation, in fact, but maybe the order is not correct. But I have one slide where I have some examples from. You can use this one with text, for example. How can you use it with text? How can we use it with time series, numerical values, and so on? So it's not very important to be images, but it's meant originally for images. I mean, the idea for convolution, it has been done originally for images. Yeah. Yes, any other questions about LeNet? This LeNet, it's very simple, but it was, I mean, invented or introduced for the first time in 1998. So it's according to the computational resources, which has been available at that time. This model was very complex at that time. But today, of course, we can have, for example, I mean, ResNet 50 or something today, 50 layers or more. But this one was available computational resources in 1998. This one was a state of the art at that time. Yes. Any other question? So if you want to build this model and use it for another binary classification problems, you just need to remember to modify this layer, for example. I mean this layer. If you want to use the same model for other problems, so you need to change maybe the second fully connected layer according to your problem. If it is MNIST, so it will be we need to have 10 units here. If it is, for example, cats and dogs, binary classification problems, you need to change this one into 2, for example. So the number of units here will be the number of classes. So it's according to the problem which you are solving. If it is binary classification problem, in this case, this one will be two values, two units, because we have 2 decisions, yes and no, for example, cats and dogs. So if you want to use it for regression, so in this case, you need to change the activation function which we are using here, and it changes the loss function, right? Maybe here loss function is cross entropy. We need to go to this example in GitHub and see how. So maybe I can open it here. So if I want to share, yes, if you can you see this one? So this is the model. So from Keras, we import sequential model, sequential API. We use conv2d, we use average pooling, flatten, dense layer from Keras.layers. We need to use this one for building our model. We need to use confusion matrix because I need to upload the confusion matrix. This is my data set. It's MNIST. How can we get MNIST? We can get it from Keras.datasets. We can get it from here, from Keras. You can get also it, in fact, from sklearn. It's nice to get it from Keras here. And it's automatically divided into 16,000 images for training and 10,000 images for testing. And each pixel value, in fact, it's a number between 0 and 255. So when you divide its pixel value by 255, we normalize it. So this one, in fact, it's normalization. So we do it for xtrain and xtest. We divide each pixel value by 255. And the output, in fact, it's one column, which has a number between 0 and 9, this one, because this is the 10 classes. So we can just use 2 categorical to convert it into one-hot encoding. So this one, it's for one-hot encoding. We convert the target values using one-hot encoding. So from this step here, this one, it's one column. After this step, it will be 10 column, right? Where it's zeros everywhere, and one when it's I mean belongs to that category, for example. So this is the dimension of my training data, or this is it's not the original dimension. This is the dimension, in fact, of the training data set. 60,000 images, each has a size of 28 times 28. And for the test, it will be 10,000 times 28 times 28. This is the model. It's not, I mean, we didn't import it from anywhere. In fact, we build it from scratch. So we use sequential API. We will have 3 layers, 3 conv layers. So the first layer, Number of filters will be 6. The kernel size will be 5 or 5 times 5. Both is okay. Stride equal 1. The activation function here, they used the hyperbolic tangent. They didn't use ReLU, in fact, because in 1998, they don't discover ReLU. So at that time, they used the hyperbolic tangent. The input shape will be 28 times 28 times 1. We use padding in the first layer. So so we should expect that the dimension will still the same after this one. And after that, we will use average pooling. The size will be 2, stride equal 2, and padding equal valid. It means we don't use padding. So when it's the same, we use padding, 0 padding. When it's valid, we don't use any padding. After that, the second conv layer. So this is the first layer. So the number of parameters here will be 156. How can we get 156? It will be 5 times 5 times 6 plus 6. So if you want to get this number, so it will be the kernel size. It will be 5 times 5 because it's 2D. 5 times 5 times number of filters, which is 6 plus 6. You will get this number. So the second conv layer, we need to extract 16 feature maps. So number of filters will be 16. The kernel size, it will be 5 or 5 times 5. Stride equal 1. The activation function is hyperbolic tangent. We don't use 0 padding. So the size here will reduce. In fact, I mean, the size here will reduce because we didn't use padding. And after that, we will use average pooling layer. So the number of parameters here, it will be 5 times 5 times 5 times 5 times 6 times 16 plus 16. You will get this number here. The third convolutional layer, we need to extract 120 features using the same kernel size, which is 5 times 5. When we apply this 5 times 5 to this one, we will get only 1 pixel because we didn't use 0 padding here. So the output from this one will be 1 times 1 times 120. Number of parameters here will be 5 times 5, 5 times 5 times 120 times 16 plus 120. You will get this number. So this is number of trainable parameters of this layer. And after that, we will flatten. I mean, the output here, it will be 1 times 1 times 120. We need to flatten it to convert it into one flat vector. And this one, it's the conv part, or the feature extraction part. It will be followed by the fully connected layer part. So this is a design pattern, in fact. So the first dense layer, it will have 84 units. We will use also the same activation function, hyperbolic tangent. And the second dense layer, it will have 10 outputs because we have 10 classes, number of classes equal 10. And the activation function, it will be softmax because we need to predict the probability that each image belongs to the same class. So this is a model summary. And after that, we will train it. The loss function here, it will be categorical cross entropy because we have 10 classes. We use one hot encoding. We will use the SGD optimizer, for example. Matrix is accuracy. We will train the model using X-train, Y-train. We can use also X-test, Y-test for validation. Number of epochs will be 20, batch size 32. So you can just play with those numbers. And after training, we will try to plot the, we need to plot training and loss in training and validation, and also accuracy in training and validation. Those figures are very important because it will help you to identify if you have overfitting problem. So those are very, very important. And it's smart, of course, to use early stopping. So I mean, if we are using, in this training process here, it will be smart to use early stopping because if we discover that the model will start overfitting, we can just stop. We don't need to continue until the end of those 20 epochs. Because now here, we will continue from epoch number 1 until epoch number 20, right? So we ended at 20. But if you use early stopping, it will try to watch or monitor the loss and accuracy in the validation, and it will stop training if the model will start to overfit. So we will get those figures. I recommend that you try to get those figures all time. And after that, we can get the confusion matrix. So this is the confusion matrix for the test set. Of course, I mean, maybe this is not not perfect way for doing training, because we used the whole testing set for validation. But maybe from the training set, you can use 10,000 images from the training set for validation. And you can just hold out the training set for the testing set for just testing, not validation, right? To avoid information leakage. Yes. Yeah. Do you have any question for this code? You have this code in GitHub. Just to try to open it and try to run it one more time, make some changes, try to achieve better accuracy. I mean, here's the validation accuracy. It's almost 99%. So it's 99% for validation and for training, in fact. So it's a very, very good accuracy, and we don't have overfitting. So this model is very, very efficient model, and we didn't use RELU. Try to use RELU and try to check what kind of accuracy you can get here, for example. Try to change this model. I mean, we have MNIST. We have also MNIST fashion, I guess. So you can just try to train this model using the from dataset. Yes. I mean, we normalized it. So we are sure that each pixel value will be a number between 0 and 1. So in fact, it's okay to use hyperbolic tangent. But maybe if you are using here RELU, maybe you don't need to normalize I mean, each pixel value, because RELU will accommodate it anyway. It will take care of those positive numbers, because when it's positive number, when its original value, it will be a number between, I mean, all pixel values will be positive values, a number between 0 and 255. So if you don't want to divide here by 255 and to normalize this one, you can just use here maybe RELU, for example. So do you have any question for the code?
Can I ask a question?
Yes, please.
The number of filters in our code is actually the depth of the CL, convolutional layer. You mentioned, yeah, filters 6 is it the
yes.
depth?
Those are the numbers which has been used in this LeanIt 5 in 1998. So this is exactly the same model which called the LeanIt. If you want to change it, maybe we cannot call it LeanIt. We can just call it its modified LeanIt. But at the time, they used those numbers. So we just use the same model as it is.
And
but of course, maybe if you change it, maybe you can get. It's similar to the application which Ahmed and Mingitauzi are doing. So maybe you can use grid search, for example, to try to optimize, try to find the optimum number of filters, right? We can use grid search, for example.
And does it use any?
Yes, Ali, you have another question.
Yeah. I want to know that, does it use any form of dropout?
No, they didn't use any dropout here. This is exactly the same as the LeanIt model, which has been developed in 1998. So this is exactly the same model. They don't have any dropout.
So how?
So we just use the same model.
How does it handle the overfitting problem? Because
no, we don't have overfitting here, because when we trained the model with MNIST datasets, you can see here that we don't have overfitting problem, right? So in fact, even with training, you can see that the validation accuracy keep increasing. So the performance increases with time. So we trained this model for 20 a book, but I'm sure that if we continue training it, maybe we can reach to accuracy of maybe 100% or 99.9%, for example. So don't have any overfitting problem here with this data set. So you need to use maybe a dropout. I mean, if you feel that your model will overfit, you can just use dropout, because it will try to limit the model capacity. We know that dropout is very important for, to stop, this overfitting. It will resist this overfitting problem by freezing some units in the training process and the adjustment. When we adjust weights, we will not adjust weights which are connected to some of those units. If you will use dropout here with ConvNet, some filters will be disabled. So we will go forward using all those numbers for calculating feature maps. But when we calculate error gradient and go backward for adjusting weights, we will not adjust weights which are connected to those dropped out units or neurons.
Can I ask you?
So dropout is in, yes, please.
How do we choose the loss as a categorical cross entropy? The loss function.
It's according to the classification problem, right?
Mhm.
Because this one, it's a classification problem. We have 10 classes, and we will try to predict the probability that each example belongs to one of those. So when you use this loss function, the performance, you can use mean square error when it's a regression, for example. You can use mean square error, mean absolute error when it's a regression problem. But this problem, it's a classification problem, and it's a multi-class classification. When it's multi-class classification, because we have here 10 classes, so it will be nice to use this cross entropy.
What about the binary classification? Can we use cross entropy for binary classification?
Yeah. Yes, I mean, I get, yeah, why not? Because it's two classes, so it's a multi-class also, right? It's multi-class classification problem. You can just say that it's a multi-class classification. We have two classes, so you can use this one. Or, so we need, maybe we need to have also maybe one slide and try to find the difference between different lost functions. What is the difference? But when it's categorical, for example, we have those 10 categories. We can use this cross entropy loss function to give us good performance.
Thank you.
This one, when it's a 0, we will not see the output. We will not print out, I mean, those numbers here. Shuffle equal 2, which means it will shuffle my data each batch, I guess, right? Each training, each epoch, it will shuffle the data set, I guess. Yes. And using history here, so when you train your model, you can just write history equal model.fit. So you will keep all those numbers into history, and from those history you will have you will have some keys here. You can store here loss, accuracy, validation loss, and validation accuracy. Loss, it's a training loss. Accuracy, it's a training accuracy, and the validation loss and the validation accuracy. You will have those numbers. You can print out mean values, right? So if you want to get training and validation loss mean values, for example, you can get it from here. Maybe mean, maximum, standard deviations. Those numbers are very important. When you are writing a paper, you need to get those numbers and put it in the table, for example. So after training your model, you need to find, I mean, minimum, maybe mean, minimum, maximum, mean, for example, and the standard deviation, for example. Those numbers will be very nice. So you can get a table from those numbers. And at the same time, also, you can get the accuracy for training, accuracy for validation, loss for training, and loss for validation. And you can use those for plotting those two curves. Those are very important because people want to be sure that your model is not overfitting. So plotting those will be very, very useful.
Can I ask one question here?
Yes, please.
Let's say that we have two different models, and one is resulting in better training accuracy, but has a little bit more of a difference with the validation accuracy. So validation is a bit lower than training accuracy. So that's for one model. And then another one, for example, has lower training accuracy, but training and validation accuracy are somewhat the same. Which one would you prefer?
So the validation in the two models are the same?
No, in the first model, training accuracy is higher than in the second one, but there is a difference between training and validation accuracy, and validation accuracy is lower. So there is like, it's like maybe like overfitting, let's say 10% of a difference between training and validation.
Yeah.
But training accuracy in that case is higher than in another one where they are almost the same, training and validation accuracy. So which model would you prefer?
Yeah. Okay, so we can see it in different way, for example. So the validation accuracy in the two models is the same, but the training accuracy in one of them is higher than the one of the two models, right? So both of them have the same validation accuracy, but they have different training accuracy. This is what you mean?
Or let's say that the validation accuracy is lower even in the second case where there is no overfitting, so there is no difference between training and validation accuracy.
Yeah, I mean, for deployment, we need to deploy the model which has no overfitting at all, because we will trust that this model will be able to generalize.
Okay.
Right.
So then better
because if it has maybe 10%. With the one with less training and less training accuracy and the high validation accuracy.
Okay. Yeah.
Because do you know why? Because when the training accuracy increases, it means that the model will overfit the training data set. So with time, the model will start to memorize the training data set, and it will just give us very, fantastic training accuracy. So the most important is the validation part here, in fact.
Mm-hmm. And
compared to the training, it should be compared. So it should be relative to the training accuracy, right? Because in this case, if you maybe you have a model with 0% overfitting, another model with 10% overfitting, so I should be sure that I'm selecting the model which has maybe 0% overfitting, because its performance in generalization, it will be much better. So its performance with unknown examples, it will be much better, and this is the most important.
Mm-hmm. Thank you.
Because we will deploy it and it will be running maybe in real time in the future. And I want to be sure that the model will be able to generalize and it will be able to correctly classify those unknown examples. So this is very, very important. So we need to check the validation accuracy against the training accuracy. And if you have a model which is, you feel that it's 10% overfitting, you have another model which is just free overfitting, you need to select the other one. So maybe the training accuracy is much less in the second one, but its performance in deployment, it will be much better, because it will have better capability, in fact, in generalization and dealing with or classifying unknown examples.
Could, for example, number of epochs be the reason that it's overfitting? Like if you do a lot of them, could they cause the model to overfit?
Yes, it will overfit. Yes, if your model has some intention to overfit, or if your model has potential to overfit, if you will keep training it, it will overfit anyway, right? So it's smart to keep it training for a large number of epochs to be sure that it's not overfitting. I need to see the performance over large number of epochs, right? But in this case, we need to use early stopping, because early stopping will be like warning us that my model will start to overfit and we will stop training at some point.
Okay.
So you can just, to be sure, to be safe, you can select, for example, a big number of epochs, for example, and use early stopping, for example, to stop training at some point if the model will start to overfit. So, for example, if I'm using here early stopping and I'm selecting 20 epoch, if my model can go from epoch number 1 to epoch number 20, it means I don't have any kind of overfitting, because early stopping could not identify if my model will overfit or not, which means my model will not overfit. So increase this number and use early stopping to be safe.
Okay, and what would you recommend for, like, I think in Keras, this early stopping has kind of like a patience or tolerance level, something like that. So if, yes, let's say, it's a parameter that has to be set, right?
Yes, yes. Because you need to, the model, maybe the code wants to know what value, how much tolerance you want to give your model for overfit. Maybe it can overfit a little bit, but not too much. So you need to decide this using this variables in early stopping. Yes. So, but also, we know that overfitting, it's a problem because of maybe maybe model capacity. So if you feel that your model will overfit, you try to reduce the model capacity, for example. How can we reduce model capacity? By reducing maybe maybe by adding more average pooling, for example. When we add more average pooling layer, we will try to reduce the dimension of the feature maps. And when we reduce the dimension of the feature maps, we will reduce number of neurons in the maybe first fully connected layer. So in this case, we will reduce model capacity. So pooling layer is very important. So you can try to add more pooling layer, try to reduce number of units in each fully connected layer, for example. In this case, you can try to reduce the model capacity to avoid this overfitting problem. I mean, overfitting problem, it's a problem about the design of the model, in fact. We designed a model which is very capable, and my data set is not that big to train, to adjust to those huge set of parameters. So the problem, in fact, it relates to us. So we just need to simplify the model a little bit. Try to put some restriction in the model. Try to make it more simple. Try to add more those pooling layers to reduce the dimension of the feature maps. And when we reduce the dimension of the feature maps, we will reduce chances to overfit. So if you feel that your model overfit, try to look back into your model, your design, and try to put some restrictions or make it more simple, for example, by adding some more pooling layers, for example. Maybe drop out, for example, add the drop out layers. So we don't adjust pool weights each epoch or each iteration, right? So we drop out some weights from the training process. So in this case, we will try to reduce the model capacity a little bit. So overfitting, it's our problem, which we need to deal with, in fact, right? So overfitting, it means you selected a model which has higher capacity than it is necessary. For example, I mean, I just selected very high capacity model for my data set. So I need to simplify the model a little bit, right? Try to remove one layer, for example, for the connected layer, maybe. Try to add more max pooling or average pooling layers, and so on.
Are we using batch sizes here or not?
Yes, why not? I mean, batch size, it's in the training process. So in mini batch,
Okay.
so I mean, it's important because it has a relationship maybe with with the memory. So you can go for we have the learning process or learning modes. We have 3 learning modes. Can you describe those learning modes? Stochastic gradient, batch gradient, and mini batch gradient. In stochastic gradient, we train the model example by example, right? Which is, they call it online learning. And in batch, we use the whole data set in one time for calculating the gradient and adjust the weights only one time each epoch. And in mini batch, it's a trade-off between the 2 approaches, right? And in this mini batch, we will decide the size of the mini batch maybe according to the memory available for us. So maybe the most optimum it's batch learning, right? I'm using the whole data set one time for calculating errors, and go back only one time for adjusting weights. So it will be adjusting weights, it will be one time each epoch. So we use mini batch. It's a kind of trade-off because maybe I don't have enough memory to deal with my whole data set at once. So in this case, we will use for mini batch.
But that could not cause overfitting, right? Even if you use smaller batch size, or could it?
I don't think it has any connection. I don't
Okay.
feel that it's because this mini batch it's about maybe the I don't think it has any problem with this overfitting problem because it's just dividing my data set into mini batches and training it batch by batch, right? So if your model will overfit, it will overfit. I mean, it will not make any impact from my point of view. But maybe you can go for cross validation if the data set is small. So if your data set is fixed, if you have enough data set, it's big enough. If you will go for batch learning or mini batch learning, for example, it doesn't matter in fact, because if your model capacity is too high, it will overfit anyway. So if you will give it small pieces, it's like someone who is eating, for example. Maybe it's like big spoon and a small spoon, right? If he's hungry, he will just eat it. So if you give him amount of food, and you give him big spoon or small spoon, for example. So someone, if he's very hungry, he will, for example, imagine someone has soap, he will just drink it one time like this. Or maybe someone else, he will just use a spoon to drink it step by step, but he will consume it anyway. So so if the model is, if the model capacity is high, it will overfit anyway, right? This mini batch, maybe it will not make any difference. But if you can go to cross validation, this is a different story. So if your data set is small and I don't want to have hold out subset of data for testing, so in this case we can go for cross validation. And in cross validation, in fact, it's one way for dealing with overfitting, because I'm using the whole data set. We are not holding out one subset for testing. We are just using the whole data set for training. So it's one way for just using the whole data set, not hold out any subset for training. So we have cross validation and hold out validation. And hold out validation, we divide the data into one part for training, one part for testing. But in cross validation, we use the whole data for training. And once we did that, we will have some numbers representing the model performance or accuracy. And after that, we will use the whole data for training the last model. I mean, the model which we will deploy, we will not test it, and we will use the whole data for training it.
Is this holdout is the one from a train test split, right? That's the one.
Yes.
Okay.
Yes, this is correct. Train test split. But if you will go for cross validation, we don't want to do this, because I don't want to hold out any subset of data for testing, and I want to use the whole data, so we can go for cross validation. And in cross validation, we will divide it into k folds, right? Number of folds, and we will train the model with k-1 and test it with k, and we will repeat this one k times, and each time we will have a kind of accuracy or performance measure or accuracy measure, and at the end we will take the average of those k times, and this average value, it will be the accuracy of the model. It will be the minimum accuracy, in fact, because we can get better accuracy, because the model which we will deploy in real life, we will use the whole data set for training it. We will not split the data anymore. We will use the whole data for training this model, and this average accuracy will be the accuracy which representing the accuracy of my model. Do you have any question regarding this cross validation and hold out validation? Do you have any question? So cross validation, we use cross validation when the data set is small and we cannot afford splitting it into training and testing. Yeah, any question?
Can I add something for means?
Yes, please.
It is written in one of the papers. The best result for accuracy of means database is 99.65% accuracy. Actually, is a paper in archive 2010. So
it was from 2010.
Yeah, I will send it to
for MNIST.
Yeah, for means.
For MNIST dataset.
Yeah.
Because here we achieved this performance, but if you can keep training, I trained the model here for 20, but maybe if you can train it for 40 or for 50, for example, maybe you can reach 99 point something, right? Yeah. So it means that the best accuracy achieved in this one is
so far
is 99 points. Okay.
So yeah.
But you said it's from 2010, yes. Which model has been used here?
It's like they use a brute force, I think, because they use a lot of as they said in the abstract.
Yeah, in this table, in this error rates and MNIST datasets, they use the 5 models. And each model, I mean, the first model has 3 layers, the second it's 4 layers, 5, 6. And at the end, they use the 9 layers model. And they can
said
achieve
that many hidden layers, many neuronal layers, and yeah, a lot of image. So this is the best if we want to if we could achieve better results, we could submit it or like publish it somewhere.
Yes. Yes. Okay. So should we go to the second model? So we will go here to the second model. Yes. I mean, last time we talked about this 1 times 1 conv layer, or this reduce layer. We talked about it. I mean, we mentioned the idea about it last time. So the idea here, in fact, is to maybe I need to make it. Yes. So, okay. So we will talk about AlexNet. So AlexNet, it was presented in 2012. And it's a series of convolutional and pooling layers stacked on top of each other, followed by fully connected layers and softmax. So, and it's similar to LeNet, but it's much deeper, where we have more hidden layers and the bigger filter size. So the filter size here, it's more and the bigger. It's just bigger, which means it's more filters per layer, more number of filters. So the first conv layer, we have 96. The second conv layer, we have 256. The third, we try to extract 384. The fourth, it's 384. The fifth, it's 256, right? So, and you can see that the size is going down from 224 times 224 into 55 times 55, and after that 27 times 27. So it will reduce. So it's here also, we try to increase the depth and reduce the size of each feature map until we end with 13 times 13 size feature maps. So the dimension is 13 times 13 times 256. So AlexNet has about 60 million parameters and 650,000 neurons, which gives it a larger learning capacity to understand the more complex features. So, and it's trained using ImageNet. So this model has been trained using ImageNet. And the ImageNet, it's a visual database designed to use visual object recognition software. It has more than 14 million images categorized into 22,000 categories. But this model, in fact, it has been designed for classifying images or objects into 1,000 different types of objects. It's like cars, trucks, chairs, tables, and so on. So this model has 8 layers. It has 5 conv layers and 3 fully connected layers. And it has been trained using ImageNet. ImageNet, it's public dataset, which consists of more than 14 million images, categorized into 22,000 categories, but also they have some subcategories or some abstract categories. I mean, at the end, it will be 1,000. I mean, this model will be used for classifying it into one of 1,000 classes. So it's 5 convolutional layers and the 3 fully connected layers. This one has been trained using ImageNet. So you can transfer this model into other problems. So if you are working with, for example, MNIST, we can transfer this model into MNIST. It's easy, right? Because it's image, and from image, we can extract maybe, I mean, there is something common. When you are working in the same domain, there are something common. So you can transfer a model from one data set to another data set. For example, we are working in plastic tracking, in marine plastic detection and declassification. And it's a different problem, in fact, but we can use the same model. We can transfer this model for solving a different problem within similar domain, for example. So So the input here, it's RGB, and when it's RGB, you can work with video at the same time. So for example, if you want to track people in video frames, for example, you can use the same model here, because this model works with RGB images, and the video can be converted into a number of frames where each frame is a single RGB image. So the problem here, you just need to transform your input image into this size, 224 to 224. I mean, there is a set of sizes here. So the dimension of the input image, in fact, here it's 224 times 224, but you can make some calculations according to the filter size here. I mean, the filter size here, it's 11 times 11. So according to this filter size, and according to the size of the feature maps here, 55 times 55, you can select the dimension of the input image. It could be 224 times 224. It could be also, there will be a range of input size. There will be a range, accepted range. So when you transfer this model from any domain to another domain, you will have a range of input size. You need to format your images. You need to transform it into this specific size. So AlexNet, we have the input image. The filter size of the first conv layer, it's 11 times 11. They use stride equal 4. We try to extract 96 feature maps. So we will get this image. So it will be 55 times 55 times 96. And after that, you will apply max pooling. From this max pooling, the size will be reduced into 27 times 27. It will be about the dimension, width, and height of each feature maps, but the same number of feature maps will stay as it is, 96. So the size after max pooling here, it will be 27 times 27 times 96. So the second convolutional layer, we will apply 5 times 5 filter, and we try to extract 256 kernels or 256 feature maps. We will apply it to this input volume, and we will get 27 times 27 times 256 images or feature maps. We will apply max pooling. From this max pooling, we will get this volume. And after that, we will apply the third convolutional layer. And from this convolutional layer, the filter size will be 3 times 3. And we try to extract 384 feature maps. So we will get this one. We will apply, it will be followed by the fourth convolutional layer, 3 times 3. And we try to extract the same number of features, which is 384. So we will get this number. We didn't use zero padding here, so the dimension, maybe we used here zero padding from this layer to this layer. We used the zero padding. So we have the same size, but not from, we use zero padding here. Yes, in fact. So after that, we will do it again. And at the end, we will have this input volume. So the output will be 6 times 6 times 6, 256. We will flatten it. And then when you flatten it, you will get this number of pixels. So this number of pixels, in fact, it should be 6 times 6 times 256. Can you test that? So it's 6 times 6 times 256. So it will be 9. It will be 9216. This is correct. So you will flatten this number, and you will feed this number of pixels to the second, to the next fully connected layer. This fully connected layer, it will has 4096 units. The second will be the same size, fully connected layer. And finally, the last fully connected layer will consist of 1000 neurons, because we have here 1000 classes. Yes. Yes, do you have any question for this AlexNet? AlexNet, you can use it as, people use AlexNet. I saw lots of papers in 2020, in fact, where people still use AlexNet. So you can transfer AlexNet because it's a pre-trained model. It has been trained. It's a very complex model, in fact, and it has been trained using ImageNet. So in transfer learning, I can just use that part, for example. I can transfer, because this part is for feature extraction. This is very important. And maybe this is the most time-consuming part, if you want to train that part. So I can just borrow this one from AlexNet, and modify this one. Maybe you can just modify this one, or even you can use it as it is and just change the last layer. So for example, if I want to use AlexNet with MNest, I can use the same model exactly the same, but I just need to change the last fully connected layer from 1,000 unit into 10, because in MNest I have 10 classes. So if you will use this one with ImageNet, you need to have 1,000 classes. But if you want to use it with a different problem, maybe it's binary classification problem, for example. Yes. Yes, do you have any question for this one? Any question for this AlexNet? So if you want to use AlexNet in any kind of problem, you can just, yes, yes. Okay. Any questions? Because people are writing in chat. Any question for this AlexNet? So the next item will be transfer learning. What is transfer learning? So in fact, transfer learning, it's example of applying. And we can use, for example, AlexNet, or we can use any other kind of pre-trained model for solving different problems. So we freeze the feature extraction part of the network and remove the classifier part. Then we add our new classifier or softmax layer, for example, with 2 hidden units. If you want to use it for binary classification problem, a pre-trained network is used as a classifier or as feature extractor when the target domain is somewhat similar to the source domain. So if you are working in the same domain, if you are working in image recognition in computer vision problem, for example, I can just transfer a model from one domain to another domain if it is similar or it is close. So for example, this AlexNet, for example, maybe I can use it for autonomous car, for example. So if I want to build a system for autonomous car, so where we can getting images from the car camera and try to classify it into maybe objects, trees, pedestrian, cars, bikes, and so on. So maybe we can use AlexNet for classifying it. Maybe in an autonomous car, we don't have 1,000 classifier, right? 1,000 classes. So I can modify this problem to fit my problem. So any transfer learning model or pre-trained model, it consists of 2 parts: feature extraction part and the classification part. So this one, it's feature extraction and classification part. So in fact, I need to modify it a little bit. I mean, the feature extraction, we will use it as it is, but the classification part, I need to modify it to fit my problem. So here in this example here, we have here 1,000 classes. But if you will use it for MNest dataset, I need to modify this one to 10. I cannot use this one for 1,000. I need to modify it to 10. So in this case, I just need to modify maybe this one, fully connected layer, and defreeze all the weights of the feature extraction. And then maybe the first 2 fully connected layers, I don't need to retrain it as well. So I can just freeze it, for example, and I can just adjust the weights from FEC7 and FEC8, for example. This is the one which we need to adjust. But it's up to you to make changes. So maybe if the model is not performing well, you can also make some changes. Even in the feature extraction part, you can fine tune it. So in the feature extraction part, usually maybe in the last convolutional layer, for example, where we are getting the feature maps, we can call it, this is abstract feature maps. Maybe you can use those abstract feature maps. Maybe those abstract feature maps are not fitting my problem very well. So in this case, I can just also try to modify the weights of the last conv layer, for example. So it's up to you to decide which layer need to be readjusted, for example. So this is transfer learning. We have here an example This example, it's from VGG16. VGG16, it's also pre-trained the model, in fact. So the model consists of maybe the bottom part, feature extraction part, we can know it's the bottom part. This one, it is the bottom, but maybe. So the bottom part, it's the feature extraction part, and the classifier part, we can call it, this is the top part. So in transfer learning, in fact, we will use the bottom part as it is, and we need to remove that part and replace it with a different classifier. Because if I try to transfer this one from its domain, because maybe this model has been trained using Alex ImageNet, for example, and I want to use it in different domain with different data set, for example, smaller data sets. So you can retrain the model from scratch. So you can import the model and retrain the model from scratch if you have enough data set, but it will take too much time from you. And maybe you will not have those kind of data set or the computational resources required. Maybe this one will need a 2 months from GPU to be trained, for example, and it will overfit if you don't have enough data set. So it's smart to just transfer this, to keep the feature extraction part as it is, and try to add a different classifier. So I will cancel this classifier because this classifier has been used for some specific problems and for different number of classes. So I can just remove this classifier and add a different classifier which fits my problem. The weights of that part will be frozen, so I will not readjust the weights here because it's I need to keep it as it is, and I will just try to train the new classifier which has been added to my model. So I will remove this classifier and I will add a new classifier. This new classifier, it's initialized with random weights, random values. So I need to train that part. So I will combine this one with this one, and I will use a data set which I have at the moment for retraining that part. Yes. So the fine-tuning a pre-trained network, if you are freezing the convolutional layers only, then you are using the pre-trained network as feature extractor and transferring all of its high-level feature maps to your domain. So as I told you, I can use this bottom part as it is, and I will freeze its weights. So I will not readjust it. So I will use the transferred or the pre-trained model for feature extraction, and I will add a new classifier, and this added new classifier must be trained from scratch. So this is number one. The formal definition of fine-tuning is freezing a few of the network layers that are used for feature extraction and training both the non-frozen layers and newly added classifier layers of the pre-trained models. It is called fine-tuning because when we train the feature extraction layer, we fine-tune the higher order feature representations to make them more relevant for the new task dataset. So for example, I have a pre-trained model and I want to apply this pre-trained model to my domain. So I will import this feature extraction part and I will remove the classifier and I will add a new classifier. I will freeze the weights of the feature extraction part and I will initialize the new classifier with random weights because this is as normal. And I will retrain the whole model using my small data set. So this is one way for doing it. So this is pre-trained feature extraction. This is maybe a new classifier or pre-trained classifier. So this one, it could be, you can keep part of it or you can just remove it fully and add a new classifier to this in this new model, for example. So that part is a classifier. It could be brand new classifier. So I'm just deleting the old classifier and I'm just designing a new classifier and adding it to the, attaching it, stacking it to the feature extraction part and initializing it from scratch and train that part. Or you can just select some specific layers. So it's not very important, in fact, to change the whole part. So I can just keep it as it is and just change maybe the last layer or the top layer, which is a softmax layer. And it's very similar to this example here in AlexNet. I can keep the whole model and I can just modify the softmax layer because the softmax layer, maybe this is the most important for me. So you can just start by changing the softmax layer from 1,000 classes into 10 classes, only that part, and freeze the weights of the feature extraction part and the first two fully connected layers. I don't need to change it as well, so I can just freeze it as well, and they train the model and test it. If the accuracy is okay, if you are happy with the accuracy, it's fine. If not, you can try to retrain some of those fully connected layers as well. Even maybe the last layer, the last conv layer, you can try to adjust the weights of the last conv layer, because this last conv layer, it will generate those abstract feature maps, high-level feature maps. So maybe those feature maps are not fitting my problem by 100%, and I need to modify it. So in this case, I will adjust or fine-tune the weights of the last convolutional layer. Yes. So this is some example to show you that transfer learning, in fact, it's very, very efficient. It's feature maps extracted from 4 models that are trained to classify faces, cars, elephants, and the chairs. So those are the images, and those are the feature maps which we are extracting. And if you can see here, for faces, we have those feature maps. For cars, we have those the same set of feature maps. They are very similar, in fact. It's just like horizontal and perpendicular lines or edges. For elephants, it's the same feature maps. For chairs, we have the same set of feature maps. If you can look into the feature extraction part, so I mean, from those 4 different data sets and 4 different models, in fact, it can tell us that it should be possible to use feature extraction which has been trained in faces for classifying elephants. Because as you can see here, we are getting here the same high-level feature maps. It's the same, almost the same. It's just maybe horizontal and perpendicular, maybe edges, for example. So we are getting the same feature maps, which means I can train a model for faces, and I can use the same model for classifying chairs or cars or elephants, right? So I can import a model which has been trained in faces and use the feature extraction part in different domain, like classifying chairs, elephants, cars, and so on. So in this case, I can use a pre-trained model in ImageNet and transfer it to any different type of problem, maybe MRI image classifications and so on. So it could be transferred from one domain to another domain without any problem. Because from this slide, you can see that the extracted feature maps are the same. There is no difference, in fact. So I can build a model for faces and use it for classifying cars, use it for classifying elephants, use it for classifying chairs, right? Maybe for faces, it's open set data set. I don't know how many classes, but maybe for cars brands, for example, maybe we have 10, 20. So I need to change the fully connected layer or the softmax layer at the end. So this is the only trick which we need to take care of. So I mean, this model here, AlexNet, it has been designed for ImageNet to classify 1,000 objects, to classify each input image into one of those 1,000 objects or classes, for example. I can transfer this AlexNet into MNIST. You can take it as a home assignment, for example, for next week. Try to use AlexNet for classifying MNIST dataset, right? We can take it for next week, for example. So you can just write down it, please, like as a home assignment. Try to use AlexNet for MNIST, right? And we will see the accuracy. I mean, we used an example today for MNIST, and we can achieve, we use the LeNet. We use the LeNet, and we can achieve more than 98% accuracy. Try to use AlexNet with MNIST, and check how much accuracy we can get from this. From transferring AlexNet from ImageNet into MNIST dataset. We need to see. And it would be nice also if you can try to plot those extracted feature maps. So in AlexNet or in AlexNet, try to plot those feature maps, those high-level feature maps from the feature extraction after 5 conv layers. Yes. So what is really being transferred from one problem to another? It's the filter, right? This optimized filter. When we train a model for a specific data set, we try to find the weights, optimum set of weights of each filter. So we have an input image, and we will apply this filter, and we will get this feature map from this original image. So the feature map, in fact, it's the result of passing the weights on the input image during the convolutional process. So what is transferred in reality, it's the optimized filter weights. I mean, when we train a feature extractor with specific data set, in fact, we try to optimize the filter weights. And once it's trained, we will freeze it. We don't need to change it. So I have those optimized filter weights. I apply it to this specific image, and I will get this feature maps, and I can apply it to different image, maybe cars or chairs or faces, for example, and I will get different feature map, right? So what is transferred in reality? It's the optimized filter weights, which, so we cannot touch it. We just freeze it because I don't want to damage those filter maps, those filter weights. I don't want to retrain it, in fact, because it takes too much time for getting those optimized filter weights. So what is transferred when we use transfer learning, in fact, it's the filter. We have here, for example, if it is here, for example, we have, I mean, after training this one, we will have a filter size here, which is 11 times 11 times 96. So we have here 96 filters of size 11 times 11. And when we train this AlexNet with ImageNet, we can find those optimized values or weights. We need to transfer those filters from this ImageNet to different kind of problems. So this is what is transferred. Yes, because I need to go to this VGGNet, for example. It's a model which has been developed in 2014. So now we are moving in time. We started by LeNet in 1998. We go to ImageNet, AlexNet, which has been developed in 2010. Now we are in 2014 with VGGNet, and it's a visual geometry group developed by Visual Geometry Group at Oxford University. And the building blocks are exactly the same as those in LeNet and the AlexNet, except that VGGNet is more deeper, in fact. It's just deeper, with more convolutional pooling and dense layers. So in fact, VGGNet, it's similar to LeNet and AlexNet, but the difference, it's more deep, in fact. We have two versions, the VGG16 and the VGG19. So VGG16, it consists of 16 weight layers. It consists of 13 convolutional layers and 3 fully connected layers. And the receptive field has fixed unified receptive field. So the filter size will be the same in all layers, 3 times 3. This is the receptive field. So this VGG16 has unified receptive field, which is 3 times 3. All filter sizes are the same, 3 times 3. So I used it, in fact, here as feature extractor for fashion MNIST dataset. And I mean, this is the base model, VGG16. And when you write weights equal ImageNet, because it has been trained using ImageNet, those 14 million images. So this VGG16, it has been trained using ImageNet. And if you want to transfer it to a different problem, you need to decide here if you want to include top part or not. This top part, in fact, it's the classifier part. This is the classifier. Do you want to include it or not? Right? So if you want to use the original VGG16, you can just include top equal true, which means I will use the original VGG16 as it is, with 10,000 or 1,000 classifier or classes, for example. So this is the input. I want to modify this one into this image, for example. I mean, it's originally made for this size. But as I told you, if you will go to VGG16 in keras.models, you will discover that we have a set of range of input shapes. So it's okay to work with 32 times 32 times 3. This one, it's RGB image of 32 times 32 image size. And this is the model summary. I want to adjust this model to my problem. So I will freeze all trainable parameters of this model, right? So now this model, in fact, when we are not including the top part, we are using the feature extractor part. We use this model as feature extraction, only feature extraction. Feature extractor, right? Because we didn't include the fully connected layers. Include top equal false, it means we are not including the classifier, we're excluding the classifier. So now I'm importing only the feature extraction part. So if I use this model as it is, in fact, the input will be image and the output will be feature maps, not decision. So in this form, if I use this base model as it is now, the input will be an image and the output will be feature maps. How many feature maps? It will be this number. I mean, maybe you don't have too much details here. So I don't know the size here. It will be 3 times 3. I don't know the feature map size. But this is the bottom part and this is the top part. When you're excluding the top part, it means we are using only the feature extraction part. Right? So so this is model summary. We will get it. So after that, I want to save the output of the last layer of VGG16 to be the input to the next layer. So I will use this model now, this base model, for generating those feature maps, and I will create a new model. The input to this model will be the output from this base model. So now I'm creating a new model here. Maybe this is not the smart way for doing it, but we will have another way for doing it. So now I'm creating a new model. So the input to this model will be flatten, to flatten the output from this base model. And I define the 2 layers. The first dense layer has 64 units, and the second dense layer has 10 because I need to modify this one into 10 categories. And just the new model will be, I use the model not sequential. As I told you before, in Keras, you can use model, API, or you can use sequential. When you use model, in fact, you can get access to intermediate values. If you want to plot feature maps, you need to use model API. So now I have this model API now. I created this base model, and I can use this one, in fact, for generating feature maps. If you want to display those feature maps, you need to use this approach. Now, the second part will be that part, and I use the model API. The input to the model will be the output from the, the input to this model will be the input to the base model, and the output will be X. The output will be X. Yes, so this is the model. If you can see here, the first part, this is VGG16 feature extraction part. That part, it's feature extraction from VGG16. That part, it's for feature extraction. And after that, I will flatten it, because here, I mean, the output here will be 512 pixel values, as you can see here. So we will get 512 feature maps, and each feature maps has a size of 1 times 1. We will flatten it, and we will stack it to the classifier. This one will be the classifier, new classifier. So the weights of that part will be frozen. The weights of that part will be frozen because it's over than 60 million weights. I cannot retrain that part, in fact. So we will use that part as it is for feature extraction, and we will adjust only, we will train only that classifier part here, those 2 fully connected layers. And I did that, and also we have the training and validation loss, training and validation accuracy. But we have, I mean, the good news here, maybe this is very complex implementation, but if you can use sequential API, it will be much easier. So if you want to use sequential API, right? So the first layer, I will just add VGG as a layer, in fact. Add the whole model as 1 layer. So we will add here VGG16, include top equal false, right? Because I don't want to include the classifier. I need to import only the feature extraction part. Weights equal ImageNet, because I need to use the weights from training this model with ImageNet. And the input shape, you need to define the input shape will be 32 times 32 times 3. So the model now, it's more simple. Flatten. So the output from this model will be flattened, because I didn't include the classifier part. So I'm using this one only for feature extraction. I didn't include the classifier part. So the output from this layer will be feature maps. So the output from this layer, it will be 512 pixel values. I will flatten it, and after that, I will add the classification part. This one, it's a classification. This one is for classification, but this layer, in fact, it's for feature extraction. So how many classes? We have 10 classes in the output layer. Now I want to freeze, in fact, the weights of the first layer, VGG16 layer. So this VGG16 layer is very compact. In fact, it's 13 layers in reality. It's 13 convolutional layers, but when we use sequential API, we try to put it as one layer, right? So this layer, I need to freeze the weights of this layer. So it will be just layer number 0 in this model, dot trainable equal false, which means we will not retrain the weights of this layer. So now it's more simple, in fact, when we have this model summary. So the first layer, it's a VGG16, in fact. The output will be 512 times 1 times 1, and this is the total number of parameters. You see? It's 14 million, more than 14 million parameters, because we didn't use the fully connected layers. So it's only the convolutional part or the feature extraction part. And I will flatten it, and after that, I will use 2 dense layers. This is the number of weights of this dense layer. It will be this number. How can we get this number? So it will be 64 times 512 plus 64, this number. So this number will be 64 times 512 plus bias value, which is 64. You will get this number. So the last fully connected layer, it will have 10 classes. Number of weights here also, it will be 10 times 64 plus 10. So it will be this number. And this is a training and validation loss. So, and this is a confusion matrix. I don't know how much accuracy we get, in fact, but I'm sure that the accuracy is maybe more than 98%. Yes. Yes, we have this code here. Please, do you have any questions? So I'm using this one with this fashion MNIST dataset. It's similar to MNIST, but it's for fashion. And we can import it from keras.datasets.fashion _ MNIST. So this is my dataset. I used here sequential and I used the model. But as I told you, when we are working with sequential, it's much easier to work with sequential. We use model only when we want to get access to some intermediate values. So for example, when you want to build autoencoder, for example, so we need to split the model later on. So in this case, it's smart to use model API. Here also, you can use model API also for if you want to plot the feature maps from the VGG16 feature extraction part. So it's smart to use a model. But if you are not interested in printing or displaying the intermediate values, you can just go directly to sequential part. How can we import VGG16? We import it from keras.applications.vgg16. We import VGG16, and this is my data set. So when we display those data sets, it's like this one. We have 10 classes, maybe t-shirts and maybe shoes and stuff like this. We have here 10 classes, and each image, in fact, it's 28 times 28 the dimension. I don't know why it's extreme. We use 2 categorical because we need to convert it into hot encoding. I did here resize. I mean, the original size, in fact, the original image size is 28 times 28, but I want to resize it because the minimum accepted size for VGG16, it's a 32 times 32. So you need to resize, in fact. So the original size of this data set, it's each image, it's 28 times 28, but the minimum accepted size for VGG16, it's 32 times 32. So you need to do some image resize. This part is very important. We do this resize because I need to provide input images, which is accepted by the pre-trained model. So the minimum size accepted by VGG16, it's a 32 times 32. So I need to resize this one from its original size, which is 28 times 28, into 32 times 32. Download VGG16 without the classifier part. So it will be just a base model. I just defined a base model equal VGG16. Weights, it's from ImageNet, and without the top part. The top part, it is a classified part. I don't want to include it. So I want to import only the feature extraction part. And you need to define the size of the input shape. It will be 32 times 32 times 3. It's RGB image. This is the minimum accepted by VGG16. As I told you, it was originally done for, I guess, 200. Yeah. So this is the minimum size. It was originally, they made it for 224 times 224 times 3. But the minimum size, which can be accepted by VGG16, it's 32 times 32 times 3. So you need to resize the input image to this minimum dimension, which is accepted by VGG16. This is model summary. If I did this model summary for VGG16, you will have all details for the 13 layers, because I didn't include the top part, right? So we have only the feature extraction part of VGG16. So now we have here 16 layers, in fact. Sorry, 13 layers. So this is the input layer. So the size here, it's 32 times 32. We will use, I mean, all filters, they have the same receptive field, which is 3 times 3. So this number, in fact, it will be 3 times 3 times 3 times 64 plus 64 to get this number. This number, it will be 3 times 3 times 64 times 64 plus 64. You should get this number, and so on. So in total, we will have around 14 million, more than 14 million weights. We will freeze those weights, because if you try to if you try to train those model from scratch, your model will underfit, in fact, because we don't have enough data set. We have here only 60,000 images for the training data set, 60,000. And number of parameters here, it's 14 million, more than 14 million. So the model capacity will be very, very high, in fact. So maybe the model will just overfit quickly, because the model capacity is very, very high, and the data set is very, very small. So maybe it can just overfit the data set very quickly. So therefore, we will not readjust, we will not retrain that part. We call it pre-trained. It has been already trained, and we will import it as it is. So we will freeze the weights of the feature extraction part, and we will use this part for feature extraction, only for feature extraction. And after that, we need to add a new classifier. So I will use this base model. The input to this base model will be the original image, and the output from this base model will be the feature maps. I will build a new model, and the input to this model will be the last output. It will be the output from this base model, because the output from this base model, in fact, it's the feature maps. I will flatten it, and I will send it to the first dense layer, and the output from the first dense layer will be the input to the last dense layer, which has 10 outputs, right? I use here RALU in the first dense layer and Softmax in the second dense layer, because I want to classify into 10 classes. So I don't know why I did it several times. Yes, number of trainable parameters here, it will be, this is the total number of parameters, do you see, for the new model, in fact. So this is the total number of parameters. This non-trainable parameters, it's the parameters of the fully of the feature extraction part. We will not retrain those parameters. So here it's classified as non-trainable because we freeze the weights of the feature extraction part. We will train only the weights of the classifier, which is 33,000, only that part. How can we get this number? This number, in fact, it's this number of weights, which is 64 times 512 plus 64 plus 650. And 650, it's 10 times 64 plus 10. I hope that this one is clear. After that, we will compile the model. We will use the loss function is categorical cross entropy, for example. We use the SGD, we use the accuracy as a metric, and I use the history equal new model.fit. I trained the model using X-train, Y-train, batch size equals 32. I trained the model for 20 epoch. So the validation data will be the test set. I will use a test set for validation. So the model has been trained, and we have those figures here. And if you can see that we will look into the accuracy. Validation is below. Do you see here? I mean, the validation accuracy, in fact, the validation accuracy, it's less than the training accuracy, which is normal. The training loss. So the validation loss. I mean the training loss, it's much lower than the validation loss. And at the end, we will have the, okay, so this is one way for building the model using model API. You can do it also using sequential API. As I told you, in sequential API, it will be very compact and it will be much easier. So here I used model equals sequential. I'm using sequential, and the VGG16 will be with just one layer in this sequential model. So I used here VGG as one layer. This is the same also. We don't include the top part, which is a classifier part. We just use this VGG16 for feature extraction, flatten, dense layer, and that is it. And of course, we need to freeze the trainable parameters of the first layer using this command. So the model summary now, it will be more compact. So from this VGG16 feature extraction, we will have those 14.7 million weights. The output will be 512 times 1. Those are the feature maps, which we get from the feature extraction part. We will flatten it, and after that, we will use two fully connected layers for classification. So those are the numbers. This is the brand new part. This one, it is a brand new part which we added to the model. And after that, we will train the model. We will get exactly the same results because there is no difference. We will get exactly the same results, but please try to, so the accuracy here, in fact, for the validation, it's 83%. It's 83%. Okay, this is the loss. This is the validation accuracy, and this is the training accuracy. 83%. This one, it's 83.6%. So maybe we need to, work a little bit with this model to achieve better results. But this is the transfer learning part. So the most important message here is that when you import a model, pre-trained model, you need to know what is the accepted image size, because it's based on the filter size. You need to decide this one. It will give you. If you go into the documentation of any pre-trained model, it will give you the range of the accepted input volume size. And if your data set is not matching this one, you need to resize it. Downsample, whatever, you need to resize it to fit the accepted range of the input volume of the pre-trained model. Yes. Yes, any question for this VGG16? Because we can leave the second part for next week, because I have a presentation and a conference after 15 minutes. So we can just, if you have some questions, we can take those questions. So do you have any question for this VGG16? Any questions? No? So it's easy to, so can you use this one for MNIST or for For example, this one, we use it for fashion MNIST. You can use it for MNIST and try to achieve better accuracy, 98% or something. In fact, here, we just imported the feature extraction part as a block, and we added a new classifier, and we trained the classifier, only the classifier. But in fact, in reality, you can go to one of those, you see here, maybe if we cannot achieve very good accuracy, maybe you can go to this convolutional layer here and we can readjust it, in fact. So you don't need, in fact, to freeze the whole block, but sometimes, because this one, I mean, the high-level feature maps, which we will extract here, it will be this one, from this max pooling. It's 512 times 1 times 1. Maybe this one, it's not suitable for my problem, and you can make some changes here, in fact. So you can just say, okay, this one, in fact, it was optimized for ImageNet. It's not optimized for fashion MNIST, right? Because now I can achieve accuracy 80%. I need to achieve 95% or 99%, and I cannot achieve it. So in this case, maybe we can try to adjust the weights of the last conv layer. Because number of parameters here, if you can see the number of parameters here, it's very huge. Also, it's 2,359,000 weights, right? So also chances, I mean, to overfit, it will be also very high if we try to adjust the weights here. But if you have enough data set, you can just say that, okay, I will freeze all those layers except the last one. I will fine tune it. I want to fine tune it to customize it to my problem. I want to extract more relevant. If you feel that the extracted feature maps are not relevant to your problem, you can say that, okay, I will try to fine tune the weights of the last conv layer, because I need to get more relevant high level feature maps. How can we do this? By maybe just adjusting the weights of the last convolutional layer. Yes. Any questions? So in fact, I mean we covered the VGG 16 in fact. So this is the confusion matrix, and I mean maybe we can just leave it for next time, talking about inception network. It's only inception modules and the GoogleNet, inception and the GoogleNet, and how can, and the ResNet as well. So we still have also, and also this ResNet 50 and those escape connections. Those escape connections, it's something, inception and escape connections are very, very important. So we can leave that part for next time. But you can try, please, you can try to maybe try to use, for example, maybe AlexNet, for example, for MNIST. I mean, we agreed on this anyway. So you can try to use AlexNet, which has been trained for ImageNet, to classify MNIST dataset, and try to achieve much better accuracy. For example, 99.9% or 99.8% using using AlexNet. AlexNet, it has been trained using ImageNet. So maybe you can start with it the next time. Maybe if someone of you can try to make it, for example, this week, he can give maybe 10 minutes presentation next week or 15 minutes, starting by presenting his solution for MNIST. So try to use pre-trained model, which is AlexNet, to classify MNIST dataset. It will be a good starting point next week. So if you don't have any questions, maybe we can just stop here, and we will start again next week in the same time. Next time we will continue finishing those, and we will go also, we will give maybe a short introduction to recurrent neural network, because many of you, in fact, are working with recurrent neural network and the LSTM. So it's very, very important. I uploaded already to Blackboard some slides. I did those slides, in fact, with help from Mingtao. So please just try to go to those slides, and maybe you can just read it maybe before next week. It will give you some idea about how can we use, what is RNN and LSTM, and how can we use it for solving time series problems. Yes, any questions for today or any comment or something? We should do this reference group again. I asked the class before POSCA that we need to have this reference group, and this reference group, they should write a report about the course, please. If you didn't do it, please try. I mean, we have 20 minutes or 25 minutes before 12. I will go out. Maybe you can discuss together about this reference group and try to find, elect maybe 2 persons to write a report about course progress and stuff like this. And if you have some comments or how can we improve it for next year and so on. Yes. So thank you very much for today. We will stop here and we will meet again next week.
Thank you.
Thank you very much.
Ibrahim. Thank you.
Thank you.
Thank you very much. Thank you very much. Thank you.
Thank you. Bye.
Thank you very much. See you next week.